Okay, hello everyone. This is Blazej Kubiak. My name is Krzysztof Kudrynski, and this is a drone. It is in the box, and the world consists of two groups of people. People from the first group will immediately take the drone out and start to enjoy flying, while people from the second group will immediately download the API, or maybe even make their own better one. Now there is absolutely no shame to be part of the first group. I have real friends that would do it, and they are nice people. Myself and Blazej, we are proud to represent the elite. After over 2 years dealing with the drone, we have absolutely no idea how to fly that thing. So a few words about us. Between 9 and 5 p.m. we work on a very interesting TomTom project whose main aim is to enable cars to drive by themselves, and our contribution here is a set of technologies that will turn the video stream and the LiDAR point cloud into a precise representation of roads, which is an enabler for self-driving cars. After work, we spend our time with our families, Blazej with Blazej's, myself with mine. And when normal people start to think about going to sleep, we dive into the world of technologies, and we have similar interests: visual computing, robotics, virtual reality, artificial intelligence. Around midnight, Blazej walks to sleep, while I sleep to walk. The project we are going to tell you about was born from passion. We did it instead of meeting friends and instead of sleeping. And in this project, the drone will learn to fly. And it will learn that skill based on what it sees. And it will see the world using a camera. So a starting point for our project is a calibration chessboard. You can have a lot of pictures like that of this very well structured object, and you can use simple algorithms to find the distortion of your camera and correct it. In fact, calibration chessboard is a starting point of almost every project in computer vision. Then you start with detecting a chessboard in the image, and then tracking the chessboard in the video. These are the hello words of computer vision. However, if you are here to see the hello world application, you might be a little bit disappointed. We cannot disagree that detecting chessboard is so interesting, and it has so many wonderful practical applications, like detecting of freaks still playing chess on a chessboard, up to detection of people walking in the street with a chessboard. And the list does not end here, but our motivation was a bit different. In these fragments of videos, you will see the drone racing. It feels so amazing to see that speed. And if you realize that these races were done, controlled manually, there is one word that is screaming in your head, and it is irresponsibility. Let's analyze one case. This is an extract from the video of a drone racing, and your task is to apply some control, not to get killed. And obviously, you know that you need to turn a little bit left and fly forward. There's a lot of time to do that. There's a lot of frames where you can make that decision. But if you are starting to worry now, you're doing the right thing. Because although there is still a lot of time to make your decision, you know exactly how it's going to end. Let us analyze this one case again. You can see there was so much time to react. Like in many other cases, which ended in a silly crash, while there were tens of frames where you can apply proper control. Tens of frames begging for salvation. Together with Blazej, we decided to put an end to that. As a user, you should only click where you want to fly, and it is the machine that should calculate all the proper low-level controls, analyzing the visual content that it sees in the image. And today we will all walk through the steps what needs to be taken to make this happen on the machine, and we will show you the test results that we performed while implementing that actually. Of course, we will not be showing you the tests from ruins like that or forests, but we will show you our tests from our modern TomTom office. But if you look at it carefully and at the right perspective, you cannot miss the similarity. In fact, we have absolutely no doubt that this TomTom building was built and meant to be our training ground. So let's start to talk about our solution. And as inspiration, let's come back to our first example. We all have to agree that we humans are just amazing. Everyone here, immediately, and without any effort, is able to spot and track the right place safe we're flying to. Everyone here, immediately and without any effort, is able to apply proper control to fly there. Everyone here, immediately and without any effort, is able to spot the emerging collisions and act accordingly. This is already amazing, but what is even more amazing, that using exactly same brain, at the exact same time, we human are able to plan our next meal and perform deep considerations about life. Excuse me. General intelligence like that is obviously out of question for today science. So we will not consider how to make the drone cook or make life decisions, but we will focus on these three tasks. And when we implement these on the machine, because the machine can be absolutely dedicated to them and not distracted by anything else like we humans are, it will quickly outperform human in terms of reaction times. So let's start with the basics. You can start with whatever equipment you want, as long as your software can communicate with it. We used AR drone, Parrot, AR drone 2, because there's a lot of open source software in the web which controls it, and we chose Drone, which is an open source framework which you can download. There's thousands of lines of code, but in fact we use just one. The move command, where you apply the tilt to move left or right, to move forward and back, the speed in change of height, and the speed of rotation. Only these four parameters, and they, in our application, will be derived directly from an image, which, for our convenience, will be decoded from using the C++ FFmpeg. And this image will be analyzed using Python libraries, including Opencv and NumPy. And the control center to orchestrate all of that, in the beginning was planned to be written in Java. And this is a whole nice system with which you can start thinking about your logic. And of course, it will evolve and change while another requirements are appearing as we go with our thought process, which will happen, and we'll come back to it later. But now, let's think about our logic. So the first level of autonomy which we want is just tracking. So when we focus on some object, we want to track them. And because we are fans of the human brain, let's think how we humans do it, how we track objects. And for that, let's analyze a nice real-life example when we go to the club full of people and we find something catchy, something that gets our attention, and we want to track that. For example, a hat. But in the beginning, for a nice start, let's imagine something more familiar, but you must imagine it really hard. Imagine that in this picture, instead of a hat, we have a chessboard. Then we would have our wonderful algorithm to track it, and everything will work fine. Unfortunately, sometimes it happens that we have to track something else. And you don't know what it is until you see it in the image. So this is this particular moment when this region gains some description. It may be the distribution of colors inside, it may be the shape of the HUD itself, it may be we may be just following the flow of pixels inside. All of these approaches are easily implemented on the machine. And the good news is that you don't need to do it yourself, because it's already done for you in the libraries. And the best one from our side is Opencv. It's a C++ library. It is available in Python. It has wrappers in Java. And in Opencv, we checked these three methods. In the min shift, in the given region, we calculate the distribution of colors, and then the algorithm shifts and scales it in the next frame so that distribution stays the same. Cam shift is very similar, but apart from shifting and scaling, there is also rotation. And finally, in Optical Flow, we will measure the velocities of the pixels themselves using nice mathematical tricks involving first-order Taylor expansion, but the implementation is not very important here because we have Opencv which encapsulates that. So out of these three methods, the best results for us empirically were using Optical Flow. So let's see how it works in action in our case. So this is our graphical user interface. You see what the drone sees and some visual augmentation of what it does. On the left and right you see arrows which will appear longer when there is something detected and to make the tilt for collision avoidance. In the bottom, similarly, you can see if there is an obstacle on the ground or near the ceiling to change the height. But of course, at this stage, these three arrows will remain 0 because we are not yet omitting obstacles. We are at the level 1 autonomy, which is tracking. So we will focus on the red circle, which is now in the center. But when we start flying, a user will click on the table on the left hand side, and this table will be tracked. And then on the top you can see the arrow which shows the rotation that needs to be applied so that we are flying towards the object that we track. So we start flying, and you can see that the object is automatically tracked, and you can see the strong desire of the drone to rotate so that it flies towards this tracked object. And if we press 1, we will start autonomous mode 1, and the drone will actually rotate and now float freely, keeping track of our object. Very easy. That's level autonomy 1. We have that. And in level autonomy 2, there is not much to add, because apart from turning towards the object, we want to actually fly towards that. So we just apply flying forward, which doesn't seem very difficult. So we tested that, and it turns out that with collision avoidance, it would be probably better. Can we have this sound a little bit more? Okay. So this is how we arrive at the third level of autonomy, which is collision avoidance. And in order to avoid risk, in fact, we need to understand the content of the image, which is two-dimensional image, and we want to understand the spatial content. And this is not easy and not straightforward. So the question we'll ask ourselves again is how we humans would do it. How do we know the spatial content that we have in front of us? And the obvious answer for that is through the pair of our eyes. So let's imagine this is a simplified diagram of our viewing system. The black rectangle is where the image is formed. So for example, the retina of our eye. The dashed line is its principal axis, and a single pixel in this image corresponds to a very little information, in fact, about the object. And to be more precise, just the ray on which the object lies, but we don't know how far it is, until we have another eye, which is quite common. And if we find the corresponding pixel in this second eye to this pixel on the left, then our brain will make some nice geometry and we will know exactly where we are looking at. This is done in our brain and we can also do it. So the question is stereo vision our answer? Well, it might be. We might change our monocamera with a stereo vision system, probably much heavier, probably much more expensive. So before you all go out shopping, let's ask ourselves another question. Are we humans hopeless if we have just one eye? Obviously not. Because while we move, our brain has memory and it is fed with multiple images, and it can be mathematically proven that if we find at least seven corresponding pixels in the two images in non-critical configuration, we are able to reconstruct both the movement that we done and also the underlying 3D structure up to a scale factor. This is done in our brain, and we can also do it in our algorithm. For example, this will be a video of my chair, and in each frame the algorithm will find some characteristic key points like corners and so on in the chair, and then their corresponding points in the next frames, and from these it will calculate the reconstructed 3D structure which will be shown on the right. This approach is known under many names like structure from motion, multiple view geometry, visual SLAM, and there is a lot of open source projects in the web. There is a Opencv implementation with which you can do some simple reconstruction, and there's a lot of books which we can read and write your own better code. If you do it right, it works just perfect, especially if you move horizontally versus the object, providing your algorithm with a lot of additional perspective information. The problem is that if you move forward towards the object, any additional projective information is very small, in fact, and it may be even so small that it can be comparable with the calibration error and some noises. And in fact, it may turn out that your reconstructed world, the error is so huge that the reconstructed world will be flat, which is not true. Some say it is, but these people are crazy. It is even worse if you rotate, because then you provide zero additional projective information. And in fact, in our case, when we fly, until we actually see an obstacle, we will fly forward and rotate only. So how can we detect it? That's a problem. So in fact, however wonderful this methodology might seem, it is not the methodology of our dreams, because we are at its worst case. Similar methodology might be to use the visual odometry itself. If you focus on the door handle and the glass, during the movement you will see that on the picture the door handle moves slower than the glass because the glass is closer. And you can use this information to to make some estimation of depth on that. But again, your horizontal motion needs to be dominant in your movement in order to make this estimation. So the obvious solution would be to deliberately add to our drone some motion, sliding motion to the left and to the right. And for us Polish people and for our friends in Russia, adding a little bit of slaloming path to our motion would probably be perfectly excused. But we would not win the race. So, are we doomed to fail? Absolutely not. And again, we will draw inspiration from the power of the human brain. Because we humans do not need two eyes to understand the space around us. We do not even need to move around. We may stand still with only one eye and have absolutely no doubt what's around us. How do we know that? from experience. From millions of images fed into our brains with our eyes, we learned to understand objects, their perspectives, their relative sizes, and their shadows. And through our lifetime experience of looking at the world, we humans need no tricks to understand the space. And as amazing as it may sound, thanks to the recent advancements in artificial intelligence, we can share this experience with the machine. And we will be using a deep convolutional neural network to pass this experience to the machine, which will understand the space. Blazej will give you some more details about that in a second, but for those of you who are totally unfamiliar with machine learning approaches, the idea is that instead of designing a set of precise rules, algorithms and formulas to classify some objects, to describe them, we will be creating a multi-layer model, mathematical model, which will accept all the pixels in the input, combine them together, and produce some output label. And to make it a proper label, we will flood it from the backwards with loads of images with known labels, and this mathematical model will tune itself so that the output for each given image is the same as the label that we put to it. That's how it will learn to detect things. But you can read a lot about artificial intelligence in the books, but today we have something better. Today we will all be part of an amazing experiment in which you will learn how you will have the intuition, how artificial intelligence works, and even more importantly, putting some light on a few concerns related to its usage. In this experiment, you will be the AI, and I will train you to perform a simple categorization task. And as every network in the beginning, you have absolutely no idea what you will be learning. I will provide you some training examples, one by one, each with a label, and during such training, you will slowly shape your brains so that finally, when I give you a test example without any additional knowledge, hopefully you will know the label. Are you ready? Let's go. I need the music. That's a pity, maybe at least a little bit of music. Also not working. Okay, never mind. Example number 1 and label. Example number 2, label. Example number 3, label. Example number 4, label. Now it's time for a test. Ladies and gentlemen, the allowed answers are yes and no, and you need to choose a label which you learned that best fits this example based on the training examples. So now please raise your hands who votes for yes. Thank you very much. Now please raise your hands who votes for no. Thank you very much. The results are 5,035 for yes and 1 for no. Ladies and gentlemen, this is a correct answer. Congratulations, you have just successfully detected a sofa. We are the millionaires. We just won the first prize. Thank you very much for your active participation. It was very important for me. But now there is something disturbing. There's obviously a sofa detected everywhere here, but there is this one guy that was blinded by some other less important features also available in this image. If there were more animal lovers in this room, we would miserably fail at detecting a lovely sofa. And now this is seriously a concern in AI, because creating a nicely well-shaped, unambiguous, and representative training set for an artificial neural network is a hard task, and it's an art. And usually, you will not know what exactly is going on inside, so you probably need a lot of training data, a great amount of training data. And as a designer, you have to make a choice if you can afford it. Because maybe, using just one example, you are able to make your intuitive algorithms which will provide a nice satisfactory answer, and that would be cheaper. In case of our application, using a handcrafted algorithm would be a pain. Because here what our task is, we have a two-dimensional image, and what we want to attach a third dimension to it, in fact, a depth. Because if we have it, we can just detect the places which are closest, using just the color, and apply proper control to avoid them, if we have this. And we will train a deep convolutional neural network to perform this task for us. But to train a deep convolutional neural network, we need training data. In other words, if we want the machine to provide us with a depth map for a given image, first we need to provide it with 100,000 of examples of this job done right. So how do we get this training data? One idea would be to take a ruler and for every pixel in this image measure the distance from the camera to the object shown in this pixel. Calculate it, change it, repeat it for every pixel in this image, and then repeat it for our 100,000 of examples. Our rough estimate for that was 300 years. Although, due to low intellectual complexity of these tasks, for hardcore agile scrum masters that would still be one story point. Still, we decided to use a different approach. In the beginning, we told that the structure from motion has a problem because we need to move sideways and we are only moving forward and rotate. But now we are gathering ground truth. We can move however we want. So we can design perfectly our path so that structure from motion works perfectly, and that's what we did. We will move some sideways, and then we will move exactly between 0 and 4 meters away from a reference object, a pillar here, hence the name Deep Pillar Learning. And we will run our structure from motion algorithm, which will provide us with a preliminary depth map. This depth map will be of floating, unknown scale, because that's how structure from motion works. But we know how we are moving, so we can take this depth map and calculate histogram of all the depths in time, localize where on this depth map we have a pillar, and because we know we are moving between 0 and 4 meters away, we can normalize it to lie between 0 and 4 meters. Then we'll have the normalization, which we can reapply back to our depth maps, and we have our training examples. So we can train our network. And to be honest, we are in love with our own solution. But you have to be aware that there are at least 2 solutions that will give you the results faster. And the first one is to use internet to download the ground truth for this task, which was prepared by someone else already, and apply it to training our model. The second approach is to use internet to download the already trained network to do that task. Anyway, now Blazej will tell you about deep convolutional neural network and about our architecture.
Hello, everyone. Hello. So, it is great to make great things from scratch. However, it's a bit wiser to use existing solution, especially if they fit really to your needs. And in our case, after digging a little bit, we found a very nice network that was trained for depth estimation. And what was really nice, not only the network structure, but also pre-trained model was available to download from GitHub. It was available in two formats. We used in TensorFlow. And what was really convenient, also authors of the network also prepared the script so we could learn how to use the network, how to load the model, how to feed our own data. So we did first tests. So we download the model, load the model, and it turned out that it is very huge. It is on around 200 megabytes. And loading the model takes around 5 minutes. And the estimation on CPU took around 30 seconds. So it wasn't acceptable for our solution. But fortunately, in our office under my desk, there is a very powerful machine with 2 GTX Titan X graphical cards. And with that machine, we could perform inference in 100 milliseconds, which gives us real-time performance for our project. So now we could just use this stuff, but we are guys that always want to know what is under the hood and how everything works. So we explored the solution, and I will try to explain some details. So the solution can be described in one sentence: deep, fully convolutional neural network with upscaling layers fine-tuned from residual network 15. And it sounds a little bit terrible, so I will demystify it step by step. So let's start with simple neural network. So probably everyone has seen such picture. It is a classical fully connected neural network where every neuron is connected to every neuron in previous layer. Connections are weighted. Weights are updated during training process called backpropagation. And the network is trained in the way to give correct output or expected output. So why we could just use such a network? So take the photo from our drone camera and feed the network. So think how many weights would we have if we take the picture and downscale it to 100 by 100 pixels. And for each neuron, we have connections to each neuron in previous layer. So number of weights would be really huge. Like too much. So imagine that you would like to update almost billion or over billion weights in every training iteration. It is so many degrees of freedom that network would never converge to the correct solution. That's why convolutional neural network comes and play a nice role in this game. So to understand this thing, we need to explain a few concepts. First is convolution. Maybe some of you remember this operation from image processing class. So on the left-hand side, we have the frame. On the right, we have kernel, sometimes called filter. And we just we are summing products of corresponding pixel values in the kernel and the frame and put result in the output. And this is a short video that shows how does it work. So we are iterating over pixels and we're just convolving the part of the frame with the kernel, having very nice mosaic results in this case. Next concept that is important in convolutional networks is max pooling. It's very simple operation for downscaling image, but with preserving most important information. And for most cases, we can assume that most important information is preserved in a maximum value pixel. That's why we are iterating over pixels, and for each 4 pixels, we just take maximum value and put it in the output. And however stupid it looks like, it works, and it outperforms other pooling layers that are sometimes used. And another concept is unpooling. It is even more stupid or even more naive. So for each 4 pixels in the output, we just take the input pixel and put it in the left top corner. So you can ask why it works, because there are just zeros everywhere else. But take to account that after this unpooling layer, we put also another convolution, which makes some interpolation and, in fact, spread this preserved information out to other pixels. So it is quite simple, but it works. And in convolutional networks, we use activation function called rectified linear unit, which is basically linear function, but it is saturated for negative values. And it was introduced in 2000, and it is biologically motivated. So scientists think that our brains works in this way. So now let's see how convolutional layer works. So in the input, we have free channel RGB image. We have 3 kernels. We perform convolution. We sum results together, apply activation function, and we have feature maps as the result. So there is separate kernel for each channel. It is quite important, because sometimes we want to extract different features from different channels. Maybe from RGB is not so obvious, but if you think the next layers, there will be different features and different feature maps, and we want to use different kernels to somehow aggregate these features. If you want to have multiple channels and in next layers, we need to use multiple set of kernels. So for 3 feature maps and 3 input channels, we need 9 kernels. So let's compare it to classical fully connected layer. So what is the main difference? So according to the number of weights, as I said, for 3 kernels, 3 by 3, we have 27 weights. If we would like to have, for example, 100 feature maps, and that is as an output, we would have around less than 3,000 weights. On the other hand, in fully connected layer, in that sample, we have just one output image, but we will need 300 million weights. So if we think about convolutional layers, they are producing feature. They are feature extractors, because using not so many weights, they are producing many feature maps. And fully connected layers are good in aggregating information, so they are used for classification. What is important thing is attention to the locality. So in fully connected layer, each neuron is connected to every input neuron from the previous layer. So the output pixel may think that, for example, pixel on the rubbish bin is somehow related to the flower somewhere else. So there is no locality at all. And in convolutional layer, locality is important. Kernels works locally, maybe in some bigger context or even bigger context, but still it is local. So now let's put things together. It is typical structure of convolutional neural network, where there are a few convolutions interleaved with max pooling layers, and this part is called feature extraction part. And there is a few fully connected layers which are meant for classification. These days, for reducing number of weights, it is quite common to remove fully connected layers at all. So adding new convolutions with pooling layers. And at the end, we have just 1 pixel image, which is the output of our network. So if you use such network for the image, we would have just 1 pixel output. So we would have just 1 depth estimation. So it is not sufficient for us. We need more. That's why we need to add upscaling layers, which are basically unpooling layers, which I told before, and interleaved with convolutions. And in this case, as output, we have full resolution image with depth prediction. So now it's quite difficult to train the network from scratch because it takes a very long time. Networks are very big. It may take weeks. That's why it's quite common to use a nice technique called fine-tuning or transfer learning. And it basically works in this way that we take pre-trained model and we change a little bit then our network and retrain it with new data. So this solution was used by authors of the paper. So they used a pre-trained model for residual network 15. They cut off fully connected layers, added these unpooling layers, and they retrained this network for depth prediction. And actually, they have got very nice results. In the middle, you see the ground truth, the reference frame, and on the right, you see depth prediction, which looks very nice, so we decided to use it. And Krzysztof will continue to tell you how we deploy this.
Okay, so let's come back for a while to our initial system design, which is already a bit complicated with the components for convenience written in different languages. And now when we add our deep neural network prediction, it becomes even worse. Because not only do we face porting everything to a Linux machine where CUDA is best supported, we also cannot just call Python scripts now independently every time a frame comes, because we would need to load the huge model of the network every time. So every, let's say, 30 milliseconds, it would kill us. So it is obviously solvable. And there are people capable to manage all these components and make them work as a perfect unity. As a perfect unity. For those who cannot, the word comes with microservices. In our project, these are probably not microservices according to the definition, but breaking our design into client-server components made our life easier. Now, the headquarters is the Python application, which is served an image from the FFmpeg service, and then it asks for this image, the depth, to the CUDA depth server, and then it calculates the necessary controls and serves them to the client, which communicates directly with the drone. So now, having this all explained, let's come to our example, the ultimate demonstration. We recorded this some time ago, and to be honest, we are very happy to be able to show it to you, because during the day of recording, we had a fire. Now, if you don't know what a fire is, the fire is a set of failures that every self-respecting developer has during the day of delivery. For us, you will not see this fire in this video, because this is the best video out of 10 or 20. And also, we are using the most secure delivery platform, statistically proven to be PowerPoint. Now, seriously, all the components works nice and smooth, but during this day we had some problems with communication, with lagging network. So frankly speaking, this is the best out of a lot of trials, but we think it's cool, so let's enjoy it. Okay, you can see the drone flying, but what's interesting is on the left, the automatic controls are applied based on what the drone understands using its self-learned convolutional neural network. You can see it is flying slowly but fearlessly towards the window, which is tracked automatically on the opposite side of the room. Whenever the blue color emerges, immediately the proper control is applied to avoid an obstacle, and we are flying towards the end. Now this is, as I told, the best. Yes, this was the best out of all the videos. So as a second example, I will show you the same video again. But now you can watch it in peace. So, according to the task defined in the beginning, we have a full system where a user only shows where they want to fly, and from then on the drone flies on its own, using its own understanding, self-learned understanding of the space. It flies on its own, which is the conclusion of what we did, but before we end, we would like to, if we offended anyone while we tried to be funny, please accept following rectifications. First of all, dogs are more lovely than sofas. Second, if there are chess players here, not all chess players are freaks. When you take your old, good, traditional chessboard, in fact, playing chess can still be a nice game. And finally, irresponsibility is fun. Two rules to remember are, first, watch out for the lamps in your office. And finally, if you happen to record a video of your drone crashing at the workstation of your boss, never show it to the public. Thank you very much. We have very little time for questions, but if there are any, you can also come here. Please contact us, send us your feedback, tweet, email, voting application. We'll be very happy to hear from you. Thank you.